Section 13.3, radiation. This is our third and final heat transfer mechanism, radiation. So radiation is the process in which energy is transferred by electromagnetic waves. Common example of an electromagnetic wave is light. So sunlight, for instance, radiates energy. That's why if you go outside on a sunny day, you can warm up, you can feel the heat coming from the sun. It's not that the sun is touching you, it's not conduction. It's not that there's some large convection currents coming from the sun to you on the earth, right? It's just the radiation energy as another method of transfer. So it turns out a material that's a good absorber is also a good emitter. So if you have something that absorbs completely, that's known as a perfect black body. So this is a block that's coated with lamp black. That's one of the darkest known colors out there. And you feel this too if you go outside wearing a black t-shirt, right? You feel the sun's warmth more. It absorbs more of the heat. And similarly, it turns out it emits more of the heat as well. Versus if you have a block that's coated in silver, the temperature of the block is going to rise much more slowly. It's reflecting a lot of the heat, the radiant energy or heat from the sun away. So it's not changing the temperature nearly as quickly. So this idea of being a good absorber and a good emitter, how good it is captured in something known as the emissivity. So the emissivity is something we abbreviate as E. It's a dimensionless number between 0 and 1. So from starting at 0, then E, and always less than or equal to 1. Right, so it's the ratio of what an object radiates to what the object would radiate if it was a perfect emitter. So it's usually somewhere in reality between 0 and 1, but if it is a perfect emitter, then what the object radiates is exactly the same as what it would radiate if it was a perfect emitter. So anytime the problem says perfect emitter, you can know that that means E is equal to 1. In every other instance, it will probably tell you the emissivity, and it'll be some value between 0 and 1. And remember, the perfect emitter is going to be like the black covered block on the previous slide. And this brings us to something known as the Stefan-Boltzmann law of radiation. It says that the radiant energy, Q, the heat, emitted in some time little t by an object that has a Kelvin temperature T, a surface area A, and an emissivity E is given by the following. Q equals E sigma T to the 4th A times T. There are a few keynotes here. First, we have emissivity. That's just that number between 0 and 1. The temperature is a Kelvin temperature. This is a key detail. This is one of the instances where we must have our temperature in Kelvin. If it is not in Kelvin, your answer will be very far off. So make sure you have your temperature in Kelvin, especially before you raise it to the 4th power. Then it'll be even more off if you have it in Celsius there. The surface area A describes all of the areas, like the surface area of that block. And then, times the time that we're interested in. Now the sigma here is the Stefan-Boltzmann constant. This is something you don't have to have memorized. It's given to you on an exam. You just have to know to look it up. Though it ends up being fairly easy to remember because it's 5.67 times 10 to the negative 8. So 5678. At least that's how I remember it. Remember, it is a negative 8th power. So this does make it smaller, which is necessary when you are raising the temperature in Kelvin to the 4th power. And this cancels out all the other units. It cancels the seconds of time. It cancels the square meters of area. It cancels the kelvins raised to the 4th power. And it leaves you with the units that we would expect for radiant energy. Joules! They come back yet again. Right, so this is our basic equation for radiation. And we can take a look at it in an example. So example 6, supergiant star. The supergiant star Betelgeuse has a surface temperature of about 2,900 Kelvin and emits a power of approximately 4 times 10 to the 30 watts. Assuming that Betelgeuse is a perfect emitter and spherical, find its radius. All right, so what do we have here? Well, first off, we have a star. You could draw a star that would probably just look like a bunch of hot gas. I might just draw a star just to help myself remember it's a star, though that's not at all what it looks like. So we know the temperature of it. So we have that, 2,900 Kelvin. And we also have the power here. That's interesting because that's not something we've been talking about yet. 4 times 10 to the 30 watts. There are a couple other things that we know, right? It tells that we assume it's a perfect emitter. Perfect emitter, that keys us into something. What does that tell us? It tells us the emissivity must be 1. It also tells us it's spherical. So we'll jot that down for now. All right. And what do we want to find here? We want to find the radius of it. So since it says it's spherical and is mentioning a radius, I'm going to actually rescind my drawing of a star and draw something that looks a bit more spherical. I think that will be more helpful in the long run. But it doesn't hurt to modify your drawings as you go. All right, and this way I can label in that radius. Perfect. All right, so if we want to find the radius, what tools do we have that might help us? Well, for one, we just got that radiation equation. So I think that's worth jotting down here as a tool, right? This Q is equal to E, which we know, times the Stefan-Boltzmann constant, which we also know, times temperature to the 4th power, which we know, okay, times the area, which we don't know, times the time, which we don't know, and we don't know the heat. So what can we do here? And how does power come into it? That doesn't show up anywhere in this equation. Or does it? We have to think back to our definition of power and remember that power is just energy over time. So in terms of heat, we can say that power is Q divided by time. Q divided by T. In other words, instead of solving this equation for heat, we can divide the T by both sides, and it will then be for power. This is a very powerful approach. Okay, so dividing by T, that cancels the T on the right side. On the left side, this is now just power. And we know the emissivity, we know the Stefan-Boltzmann constant, we know the temperature. What about the area? How does that come into play? And can that relate to our radius? We can remember it's spherical. If it's spherical, that should tell us about the area, right? The key here is we need not the area of a circle, but the surface area of the entire sphere. And so for the surface area of the entire sphere, that's going to instead be 4 pi times r squared. Right, so now we're to the point where we know everything and we're able to solve for radius. So let's take a look at the cleaner solutions now that we have that set up. Okay, so with our radiant heat equation and the area is 4 pi r squared, we plug in that area, 4 pi r squared, and then we are going to solve for r, right? Keeping Q divided by T, we know that that is our power, divided by 4 pi, emissivity, Stefan-Boltzmann constant, temperature to the 4th, which is in Kelvin, so that checks out. We don't need to convert it. And if we remember to properly raise that to the 4th power, can't forget that, multiply everything in the denominator and divide that by the power in the top, take the square root, you should get that the radius is 3 times 10 to the 11th meters. That's huge, right? But that's something that we can actually measure and detect. So this is a really neat way that we can estimate the size of stars just by knowing how much power they emit. So by studying their radiation, we can then know their size. Super neat. All right, some other cool applications of this that you may have seen is if you have a thermos, right? Hydro flasks are common examples. It minimizes the heat transfer using all three methods. So conduction and convection are minimized by having evacuated surfaces, basically very little air inside here. So hard to get heat to flow through. And then there's also these silvered surfaces that allow whatever hot or cold liquid is in there that will keep the heat from flowing outward. And you want silvered surfaces on the outside too, that you don't want the heat flowing through. So that minimizes the radiation that we would have. So that's one cool application. Another cool application is a halogen cooktop stove, which is a very different one. It's not like your standard hot burner or a gas burner. It creates electromagnetic energy in the infrared range. And so then that energy passes directly to the bottom of the pot, which is really cool. It doesn't feel hot to the top, to the touch. You need special pots to absorb this radiant energy. But you can take advantage of the radiation as opposed to needing this traditional conduction like we'd use with a electric burner. So this highlights just a few of the applications of our heat transfer mechanisms, which we saw were convection, conduction, and radiation. That is chapter 13.